Hi, this is our attempt to do Lab 15 remotely. Now Lab 15 looks at red blood cells, hemoglobin, and uses anemia as a case study. Lab 15 is actually pretty laborious and has a lot of different things going on. So what I'm going to try and do is walk you through a couple of the pieces and show you some close-ups of how this would typically work in an in-class setting. Now, a hematocrit is going to be where we take some blood in a small capillary tube, so I have my small capillary tube here, and we take some blood and it's going to draw up in this capillary tube, and then I'm going to use this hematocrit centrifuge to spin it down. Now, what's going to happen is the blood is going to separate out into its red blood cells, which are heavier. They're actually going to get pushed down. And then the plasma, or the watery component of blood, is going to stay at the top. So it will separate our blood out into the cellular elements, which includes red blood cells, white blood cells, and platelets. But as you hopefully know from lecture, most of those cells are red blood cells. So we can use the cellular layer as an approximation for red blood cell amount, and the watery component, which is plasma. So again, we're going to separate out the blood into the cells and the plasma. All right, let's watch. All right, now that I've collected my blood, I'm going to go ahead and put it in the centrifuge here. And I'll spin it down, and then we'll take a look at the results. All right, it needs to spin for about 3 minutes. Okay, so the centrifuge spun for 3 minutes. Now we're going to unscrew it and take a look at my blood. So here's my blood there. But now what we're going to do is we're going to use a hematocrit reader to look at the percentage of my blood that is the dark stuff, the red blood cells. So there's a dark area below and a light area on top. The light area is the plasma. The dark area are the red blood cells. Now hematocrits are read as percentages. So what it means is we're looking at the percentage of the total blood that represents the red blood cells. Now remember, the vast majority of your blood cells will be red blood cells. So even though all of the cells are going to be compressed at the bottom of this hematocrit, since almost all of those are going to be red blood cells, we can use that percentage as an approximation for red blood cells. Now remember that red blood cells are little more than just cells containing hemoglobin. In fact, red blood cell anatomy is specialized to just be, I call them glorified packets of hemoglobin. So we get rid of all of the other cellular organelles and keep very little else except hemoglobin in there. So if we assume that's true, then this hematocrit will give us a look at our hemoglobin concentrations in our blood as well. So now we're going to learn how to use the hematocrit ruler to measure your hematocrit. So what you're looking for is measuring the percentage of your blood that is red blood cells. Now to do this, we're going to use one of these hematocrit rulers, and they're broken up to 0 to 100%. And positioning your capillary tube on this ruler is critical. So the first thing that you're going to do is take the interface between the clay sealant and the blood and place that along the very bottom line of that ruler. Then you're going to roll the hematocrit capillary tube up until you get to match the very top line with the top of the plasma as shown. So now I'm holding it in place where those lines match up. And now what I do is I take a look at where does my red blood cell transition to plasma, and I follow that line out to the numbers on the far right side, and I find out that I'm between 30 and 40% or about 38%. Here's a look at a slightly different version of that hematocrit ruler. Same idea. You need to match the clay sealant with the very bottom line, and then what you're going to do is run the capillary tube until the very top of the plasma is going to hit the very top line as shown there, and then you use this adjustable line to match it to where the blood turns into the plasma. Follow that line out and it gives you the number. So in this case, the number looks like it's probably around 38 to 40. Now we're going to apply what we've learned to today's lab. So in today's lab, you are investigating the causes of anemia. Anemia is defined by having a hemoglobin concentration that is too low for that sample of blood. In today's lab, you will be given 3 blood samples. Sample A is normal, while samples B and C both exhibit anemia. You are going to use a combination of hematocrits and red blood cell count to determine the cause of anemia in samples B and C. So to get started, we're first going to show you a set of pictures of samples A, B, and C on their hematocrit rulers. Your job is to determine the hematocrit percent and record those numbers on page 3 of Lab 15. The other piece of information that this lab acquires is what is called total red blood cell counts. So in order to determine how many red blood cells you have in a small drop of blood, a microliter of blood, you first have to do a dilution of your blood sample. So in this lab, there are actually 3 different blood samples. There's sheep's blood, so it's not typical human blood. But I have a sample, this is sample A right here. I have a sample that is considered to be normal. And then I have 2 samples that are anemic. So remember, anemic samples mean that they're not going to have enough hemoglobin in them. There are quite a few causes of anemia, including not getting enough iron, since iron is a limiting nutrient to build hemoglobin. If you don't have enough iron available, you're limited to how much hemoglobin you can build. The analogy would be if I ask you to build 10 cakes and I give you unlimited flour but only 2 eggs, you'd say, well, I can't really make 10 cakes until I get more eggs. So in the same way, you can only build as much hemoglobin as you have iron for. So iron is often limiting. For this reason, if you don't have enough iron, you won't build enough hemoglobin, and that's called iron deficiency anemia. So that's one potential cause. Another potential cause is that you have enough iron available to build hemoglobin, but you just don't have enough red blood cells. There could be a number of causes for this as well. People with leukemia sometimes don't make enough red blood cells. If you have something like sickle cell anemia, there you start making enough red blood cells, but because the hemoglobin is made differently, the red blood cells are much more prone to lysing, and so you have lower red blood cell counts. So it's not enough to just do a hematocrit. We also need to do a red blood cell count as well in order to determine, the cause of anemia. So for the red blood cells, what we're going to do is we're first going to do a 1 in 200 dilution. There are far, far, far too many red blood cells in this drop, even a microliter, to count on a slide. So instead what we're going to do is we're going to do a 1 in 200 dilution where I take saline solution that has 995 microliters in it, and I take 5 microliters from this and put it in there. And then I have my diluted sample. You can see that's much more dilute. Now what I'm going to do is I'm going to load this up on a special slide called a hemocytometer. The hemocytometer is going to take 10 microliters of this diluted blood and spread it out over an entire plane on the slide. Now the slide is such that there's actually etched lines in there, and it makes a grid of sorts. Now there's still too many cells to count all of the cells that will be on the slide, but what we can do is take a random sample using the grid technique. So next I'm going to show you how to load up a hemocytometer. Okay, so now that we've loaded up our hemocytometer with our diluted blood, now we're going to put it under a microscope, and I'm going to zoom in and show you where you need to be counting. So this is an image that shows the red blood cells spread out over the hemocytometer. And you'll notice that there are a ton of them. It would take a very long time and probably give you a substantial headache if you tried to count every single red blood cell that you see in this image. So instead we do a sampling procedure where what we do is we say, well, if we assume that the red blood cells are spread pretty evenly across the entire slide, then what we can do is we can just sample some parts of the slide and then extrapolate the total red blood cell count from the areas that we sampled. So traditionally on a hemocytometer, the areas that are picked are shown in the black boxes. These are just arbitrarily named boxes 1, 2, 3, 4, and 5. So you're responsible for counting the number of red blood cells in each of these boxes. So the first thing that you'll notice is that when you actually look at any one of these boxes, that one box is actually divided up into 16 little boxes. So you still have quite a bit of counting to do even in one box. So when you get to one of those boxes and you pull them up, there's some rules about counting. So first of all, you're only counting within the internal line right here. So notice that there's actually 2 lines on each border. You're going to ignore the external line and just count on the internal line. But that said, what happens if you have a red blood cell that falls on the line, like this one right here? Well, you might count that one, you might not. So in order to normalize, what we'll do is we'll pick any 2 lines. Usually I pick this line down here, the leftmost line, and then the bottom line. And if a red blood cell falls somewhere on that line, or I'm sorry, those 2 lines, I count them. And if they fall up here on the top or down on the right side, I don't count them. So let's take a look how we can count. So here's a little bit blown up area, and what I'm going to do is show you just how to count this upper left box here, sub box really. So what I'm going to do is I'm going to use little X's to denote that I've counted that. So I've counted this one, then this one, 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 this one. Notice I didn't count this one up here because it fell on the top line, and I said I'm not counting that top line or this right line, but if a red blood cell falls on this left line, like this one right here or this one, I would count those. Okay, so then I'm going to mark how many red blood cells I counted just in this little box here, and then I would move over to this next box and do the same thing, and the next box and the next box. And then you would basically add up all of these numbers here, and that would give you the total for a single box. Then you have to do that 4 more times in order to get the total red blood cell count for that sample. Once you have the number of red blood cells counted, and as you will see, there's a lot of red blood cells, then what you're going to do is you're going to add those numbers back together of the 5 boxes that you count, and you're going to follow the procedure described in the lab to figure out how to back calculate the total number of red blood cells. Now, in a typical human sample, the total number of red blood cells is somewhere around 5 million per microliter. But oddly enough, for whatever reason, we don't use microliter when describing red blood cells or any blood cells. We use millimetered cubed. Now, way back in lab 1, you learned that 1 microliter equals 1 millimeter cubed. So those are equivalent. So when I say 5 million, I could say 5 million per millimeter cubed or 5 million per microliter. So once you guys have that data together, then it's going to be your job to figure out why samples B and C are anemic. Is it that they have enough red blood cells, but the red blood cells must just not carry enough hemoglobin in them? Or is it that they have too few red blood cells? I'm going to briefly show you how to calculate your total red blood cell counts from squares 1 through 5. You're going to put the total number on the top and then divide it by 0.02 millimeter cubed, because that's the space that you actually measured in. And then you're going to multiply that by the original dilution factor. So remember, we did a 1 in 200 dilution to start with. So the real concentration of red blood cells is going to be 200 times whatever we count on the slide. So we need to account for that dilution factor, and so we're going to multiply by 200. To give you a quick example, let's say the total number of counts that you came up with for sample A or C maybe was 1100. And I don't actually know that that's the real number, but let's just say it is. Then you would put in 1100 divided by 0.02 millimeter cubed, multiplied by 200, and you would get 11 million red blood cells per millimeter cubed. Now, if that seems like a lot, it is. Remember, we were using sheep's blood, not human blood. So sheep have smaller red blood cells and more of them. Part D of this lab asks you to calculate out mean corpuscular volume, which is just a fancy way of saying the average size of a erythrocyte or a red blood cell. Now, remember, erythrocytes are smaller than typical cells, and they have been anatomically modified to eliminate most other bulky organelles and instead pack in as much hemoglobin as possible while still retaining their small size and large surface area. So mean corpuscular volume is a fancy way of just saying how big are your red blood cells. Now, most people have red blood cells in what is called the normal range. The normal range is anywhere between 82 to 95-ish. The units, don't worry about the units, but that's the number that we're looking for a normal size. And if you have smaller than normal red blood cells, that often indicates iron deficiency anemia. Remember that if you have iron deficiency anemia, you don't make enough hemoglobin. So when you get ready to make a red blood cell, you should be packing in almost 250 million hemoglobin molecules, but you don't have enough iron to make 250 million hemoglobin molecules per red blood cell, so you don't put that much in there. And since there's not as much, the cell shrinks around the existing hemoglobin and therefore is smaller. Likewise, you can have enlarged red blood cells, which can also indicate problems. If you have a hematocrit that indicates anemia, a lot of people immediately think that that reflects a low red blood cell count. But I'm actually going to show you that that's not always the case. You can have a normal red blood cell count, a low hematocrit, simply because the individual red blood cells are smaller. And that's shown in this diagram on the left. Because remember, hematocrits are packing the total volume. So how do you calculate MCV? So this is my own data, and there are some pieces of information here that I want you to look at. You might notice that I have my red blood cell counts are within the normal range. I have 4.6 million red blood cells per millimeter cubed, or microliter. My hemoglobin, you can see, is below normal, so that indicates that I'm anemic. And then my hematocrit is also below normal. So this was actually taken about a year and a couple months ago. And interestingly enough, this is the piece of data that my physician used to get me an endoscopy and have me tested for celiac disease. He said, you know, you're anemic. And I said, yeah, I'm always anemic. He goes, no, you're really anemic. And you're anemic as in iron deficiency anemia. And that indicates that if you're eating enough iron, but you're still deficient, that indicates a problem with your absorption. Sure enough, he was right. I did get diagnosed with celiac disease. My absorption in my intestine was poor, and so even though I was eating enough iron, I wasn't absorbing it. It turned out there were a whole bunch of other vitamins that I was really deficient in as well, so it was the combination. But this was the first one that he looked at and said, I'd like to get you tested for celiac disease. So it's kind of interesting that this ended up being useful in my own diagnosis. All right, how do we calculate MCV? So MCV is your hematocrit, and that's a whole number, times 10 to the 7th over your red blood cell counts. So in my case, my hematocrit is going to be 35.8. I'm going to multiply it by 10 to the 7th, and I'm going to divide that by my red blood cell count, which is 4.62 times 10 to the 6th. So my 10 to the 7 and my 10 to the 6 cancel out. And if you know that, then you can simplify this as 358 divided by 4.62. And if you plug that into a calculator, you get 77.49, which is exactly what my data showed. So my red blood cells are too small, a hallmark of iron deficiency anemia. Now remember, you're dealing with sheep's blood when you're going to do your own calculations for samples A, B, and C. And so their numbers are not going to approximate human numbers because they tend to have pretty small red blood cells. That said, if you happen to get an anemic sample where the red blood cell counts are pretty normal, but the MCV levels are small, that indicates iron deficiency anemia. So go ahead and calculate out your MCVs for samples A, B, and C.